EE-341 linear control systems. Up to now, we covered the root locus and rules of the root locus, and we uh, also defined some additional points related to like breakaway and break-in point, and how to find the gain when the point is given. In the last lecture we covered and we find the values of k at the breakaway point. And so starting from the definition of root locus and then the rules of root locus and how to sketch and draw the root locus, and to refine the root locus there are some additional points that like breakaway and break-in points, and how to find the value of k when point is given. And now in this lecture we will try to cover the topic of how to find the y axis crossing mm, criteria, and how to find that axis, because that vertical axis, if the root locus is crossing that vertical axis, it means system is oscillatory, showing this oscillatory behavior. And then the angle of departure and angle of arrival concepts, which are linked to the some complex poles, and up to now we are taking on the real axis poles, but if we have some complex pole in an open loop transfer function, then how to uh, find the root locus, and these concepts are linked with the departure of angle of departure and angle of arrival. Hopefully this will be the last lecture of the analysis, and it is under the CLO2. On the real axis, when there is two poles and there is a root locus lies, and there is some point in between that two poles on the real axis, that point between the two poles on the, which is the part of a root locus, is a breakaway point, where the two path of the two poles of closed loop poles uh, are combining and move away. And similarly, when there is some two zeros and there is a root locus line between these two zeros on the real axis, then that point, there is some point in between the that zeros. This is the break in. We extensively study the how to draw the root locus, and now we are showing that this type of is root locus. Here there is only two zeros in a root in a closed loop transfer function. That it means we required the some torts behavior, which is the help or guideline for the path of root locus, and we extensively study. And how to find the value of k, this is also the part of last lecture. When the open loop transfer function is given, we have then characteristic equation from the closed loop transfer function, which is the denominator part of the closed loop transfer function, and by taking the first derivative of k with respect to x on the real axis, when s is on the just far real axis, then we can find the value of k. So by taking the LCM in these equations and taking the first derivative, and denominator part is going to 0, becomes 0 after multiplication, and dk by ds equal to this one, and dk by ds at that point is 0, because this is the some maximum value of k, and after that value of k is increasing further, and then poles in a then the system shows the underdamped behavior, and system poles are in a complex plane. So here we find that s is equal to minus 3, which is on the real axis. So this minus 3 is a break away point or break in point. We can verify through by taking the just second derivative of these equations, and we find that second derivative is negative. So this is the, for example, this point is between the breakaway point is between the two poles, open loop poles. So this is the some maximum point. After that slope is decreasing, so second derivative is negative. In this example, with the same example, with the same parameter, with the open loop transfer function, we find that we define the criteria how to find the value of k when the point is defined. So this point is a breakaway point. In the 32nd lecture, we take some complex values of s and find the values of k, but here we are taking the some non-value which are we find in the last slide. So this is the on the real axis. So how to find the value of k? Just taking the characteristic equation and by taking the mod value of that one, and this is equal to 1 over g and h mod value. And we just for reminder, it is equal to the product path length of the product of poles. For example, there are pole a 1 2 3, path of that, and divided by the length of the zeros, product of length of the zeros. So it is equal to 1 over m. So in this case, by just taking the transfer function, and so if we substitute transferring here and we're taking s is equal to -3, we find that k is equal to 1. So at breakaway point k is equal to 1. This example is different from the previous examples, and how to draw the root locus for this open loop transfer function. And this shows that this is some DC value or some constant value, which is the some dynamic constants, and one pole is at 0 and other two poles are paired in the complex plane. So this is the representation of this one. So how to draw the root locus? And starting from the reviewing that how many branches are there for this root locus, because there are two poles and there is no zero, so there are three starting points for the root locus, and there will be symmetry after drawing the root locus and where the root locus lies. So now this is very important. So for example, in this region there is no root locus because there is no zero and poles on the right hand side of this region. And if we consider this region, then we have a one pole on the right of this region. Then the sum of the poles and sum of the zeros is equal to odd, which is in this case is 1. So there is root locus. And what about in this region? If we see that there are three poles on the right hand side of this region, so what is the what is the uh, what is the region where is the root locus is lies? So root locus actually lies in this region by showing this bold line. So because there is a odd uh, sum of odd poles and zeros is odd, so this blue line representing the existence of root locus. So this is a new point, and starting and already covered that here k is 0 and also this k is 0, and again this k is 0 from here, and again k is 0 simultaneously is equal to 0. So there is no 0 uh, in the open transfer function. So how to find the behavior which is going we can guess that this behavior going toward the some infinite point. So we require the some asymptotes to guideline for the behavior of root locus towards the infinite. So first of all, we have to find the values of center. For example, in this case, position of the one pole is 0 and other position of other one is at -2 and -j2. and the position of other pole is at -2, and complex part is J2. So this part is will be going 0, and we have some real value. And in the denominator part there is 3 poles, no 0. So this point is lies on the real axis. So this point lies on the real axis. So this is again an important point. So center of the asymptote is at -1.3. For example, there is some 1 and there is some point where -3, -1.33. So this is the center. And what are the angles? So one angle is, and for k0, and k0 varies from 0 to 1 and 2. There are 3 values of k. So for k0 there is angle pi divided by the 3. So angle is 60 degree, and for next value of k, angle is 180 degree, and for the third value of the angle is 300. So these are the 3 values related to the asymptotes, and we have the center of the asymptotes. So up to now we have a open loop transfer function, and we find the center of the asymptote and the angles related to the asymptotes. So how to find the value of k? This is the criteria, and first of all we have some closed loop transfer function, and after finding the closed loop transfer function, which is kg over 1 plus k g of s h of s, and this part is the characteristic equations, and this part is called the open loop transfer function, and this characteristic equations is equal to 0, and actually we are finding the roots. So in this way we can find the value of k. So just taking the LCM, and by taking the LCM or directly we can find this relation by using this situation, and then taking the first derivative, which is equal to -3 s square minus 4s minus 8, and according to the criteria, when put equal to 0, dk by ds first derivative equal to 0, then we have two values. So these values are lying in the complex plane. So this s is at somewhere at plus for example here and here, this is -1.333. So there is no breakaway point, because there is no value on the real axis. So there is no breakaway point. So this is the first time we are finding this type of result. This is very interesting case. So we covered the 6 points or rules or, or ways to find the root locus. And in the last point we find that when we solve this equation dk by ds of a characteristic equation, and we find that there is no breakaway point, because there is no real axis point on the for that situation, which when the open loop transfer function is given in like this one. So next is uh, how to find the criteria for value of k. So how to we can discuss the whole situation for the value of k. Again, this is a simple, as we already covered the stability chapter. Actually, when we're talking about the k related to the stability factor, then stability criteria already covered is applicable here. And when we are talking about the transient analysis and some system design parameters, then we can also discuss in that point of view. But here we are talking about the stability criteria. So we have characteristic equations. So it is equal to 1 plus k transfer function over is is s times s plus 2 plus j2 times s plus 2 minus j2. So this is the characteristic equation, and from this characteristic equations we simply find the this polynomial. So now we have a polynomial, and so this is the equations, and from the equation this polynomial can be find the stable can be we can apply the criteria of stability on this polynomial, because this is already covered. So quick review of this one. First of all, we have to uh, and develop a row table, and this is the sum. And what is the way of row table? Just taking the coefficient on the left hand side and starting from the higher one, which is s raised to power 3, and going to what the s raised to power 0. And in the next column, first row is filled by the first coefficient, and second column of first row is filled by the alternate uh, alternate coefficient, skipping by 4s square. So 4 is putting in the second one, and next row is k. Just applying the criteria, and we find that there is no, this relation is dependent on the k. And similarly, if we apply the same criteria and we find that case here, so we can discuss the stability in this point of view. For example, if this is equal to 0, for example this is equal to 0, then k is 32. When k is 32, then this coefficient is 0. It means system is marginally stable, and system showing the oscillating behavior as sustained oscillations. So when we taking the values is equal to k, which is the some maximum value we can take for the stability. If we increase the value of k further from 32, then system will be unstable, and before that system is stable, and at k equal to 30 it is equal, systems maintain its oscillations. And how to find that oscillations frequency? So when it is equal to 0, then we are normally considering the uh, we are taking the polynomial of the above of that zeros, that is the special cases already studies of the route table. So so it is equal to 4 s square plus 32, and by solving this equation we find that s is equal to this one, and it means we have this oscillations, we have this oscillation which is the some maximum oscillations linked to these values, and also it is dependent on the values. Okay, so it means systems is showing the oscillator behaving when the poles lying on this one, closed loop poles lying on this vertical axis, and where k is equal to 32. And further, if we increase the values of k, then definitely systems will be unstable, and before that, before this 32 value of k, system is stable. Angle of departure: when there is a pole in a complex plane, and at what angle, and these are the open loop poles. So at what angle the poles are leaving by the root locus. So that angle is called the angle of departure. And what is the formula to find the angle of departure? It is equal to 180 minus it is the difference between the poles, sum of the poles at the given point, and minus angle uh, of the zeros at the same point. For example, first of all, we discuss this some angles. For example, we are talking about this pole, which is at somewhere at minus sigma plus j omega d, and we want to find the angles. For example, other open loop poles are lying at these points. Then we have to find the angle. This is the angle, for example, theta 1, and similarly this is the theta 2. So here we will put theta 1 plus theta 2, and similarly for the same pole, and we will continue for the every complex pole. And similarly, if there are two zeros, maybe one zero and second zero, and directly connected with the considering pole, then find this angle, which is maybe angle 1 prime, and similarly, for example, in this case it is 90, theta 2 prime is equal to 90. So here we will put theta 1 prime plus theta 2 prime. So this is the way to calculate the sum of the angles of at due to the that complex pole, due to the zeros, and similarly due to the other poles, and taking the difference of this one and then subtract from the 180. And similarly, angle of arrival is the, if the open loop zero are in a complex plane, at what angle this is approaching by the root locus, so that angle is called the angle of arrival. And its definition is, how to find the angle of arrival. It is equal to 180 minus, so this is the difference between the zeros angle, sum of the angles of zeros due to the given zero, and similarly minus sum of the angles of poles due to the that same zero. For example, how to find this one? For example, we are considering only this pole where k is equal to infinite. So this is the open loop zero, and if there are other zeros, maybe there are one zero is here and other zero is here. So find the angle which is theta 1 prime, and similarly this is the theta 2 prime, and here we will take the theta 1 prime plus theta 2 prime minus. So how to find the angles due to the poles? By considering that same zero. For example, we have two pole, one pole is here and other pole is here, and connected by this one, and this is the theta 1, and similarly this is the angle we have find here, and say it is theta 1 and this is theta 2. So here we will put theta 1 plus theta 2. So this is the sum of the angles at poles due to the considering complex zero. So this is the way to find the angle of arrival and angle of departure. We will try to cover in an example. So continuing with the same example, here let's again draw the transfer function. There are one pole is at the origin and other two poles are in a complex way. So because there are only complex poles, there is no complex zero, so we consider the concept of angle of departure for we will find the angle of departure for both complex poles, and at what angle this pole is departure when we vary the values of k. So this is the simplest way. We can even use the geometry to find the angle, but this is first of all, and this is the pole. So if we consider this pole, of position -2 plus j2. If we consider this position, so what is the sum of the angles of this one? So this is some angle, and similarly this angle. So what are the angles? So we can even directly find from the transfer function, um, just taking the transfer function, and we are going to find the values of s at this point, and we are just considering the phase angles. We are not talking about the magnitudes. So in this if we put s is equal to -2 plus j2, and similarly if we put this one, then this 2 and this plus 2 and -2 will be cancelled out, and the it is j 4, and similarly this is something -2 plus j 2. So this making the angle 135, and this term making the angle 90. So sum is -2 to 5, and in the numerator form this is equal to this one. And according to the definition, we just put here 180, and sum of the angles of poles, there are no zeros, so uh, it is equal to the -45. So this is the angle we have find. And similar, in the similar way we can find the angle of departure for the another pole, which is at -2 minus j2, and this angle is plus 45. So these are the asymptotes, and this is the center, and we will find here that there are two complex poles. So two angle of departure, one is at -45, another is at +45. How to draw, or how to take the help from these angles to draw the actual diagram? Let's see. So by using the parameters we are finding here, that in the given transfer function we have three poles, and we find the center of asymptote here, and the guideline or the asymptotic lines are making the angle 60, 30 and 180, and the blue lines representing the asymptotes, and then we find the angle uh, of departure at the at this pole, which is at -2 plus j2, and similarly at this pole at -2 minus j2. And so through these guidelines now we can draw the root locus. So root locus is starting from here where k is 0, and again starting from the open loop pole k0. These are two complex poles, and then follow the asymptotic lines, and similarly starting with this angle and draw with freehand. And the third pole, root locus for third pole, which is at k0 when it is at origin on this axis, and again it is starting from the k0. So this is the root locus, and this root locus draw we can verify through the MATLAB. And this is this root locus, this blue line is due to the root due to the open loop 0 at origin, and this green line is the root locus due to the at -2 plus j2, and similarly this red line is due to the minus j2, and it follows the same routes. So these are the guidelines, and similar way we can find the other transfer functions, root locus of the transfer functions, when the poles are in a complex plane and zeros are in a complex plane. So This is the example, and you can try the different examples. And this is the summary here. In this main root locus topic, starting from the some simple examples, and we find the root locus of some complex planes, and how to sketch where the real axis root locus is lying. We find that for negative feedback, if the odd number total number of zeros and poles on the right half of that region is odd, then for the negative feedback, then there is root locus on the real axis. And similarly, if the root locus starting from k0 and at k infinite, which is the open loop 0, if it is not happening, if the number of poles are larger, which is our in general case, then what are the guidelines to draw the root locus? Then we take the asymptotes and find the center of asymptotes, and then angle of the asymptotes. And similarly, we find the parameter k, and there are a lot of discussions like the stability factor, and we develop the row table, and from the row table we find that uh, find that uh, if the if we find the some specific condition at some specific values of k, systems is oscillating behavior, and for the stability, and that value should be less than that critical value. If we change the value of k greater than that value, then it is the unstable system. And similarly, uh, if we find the value of k, then we can find the frequencies relevant to that points. If the points are fixed and the values of k are fixed, then we can find the frequencies relevant to the different points. For example, on the vertical axis and imaginary axis, what are the frequencies? um, so in the previous example, we find that there are mathematically there are two or three ways to find that value. Just taking replace s is by the frequency, and sigma is 0 on the imaginary axis, and we have the k value using the transfer function, and just putting the values and then solve the some algebra, and then we find the frequencies. And the last, if the complex poles and complex zeros are there in open loop transfer function, and then how to draw the angle of departure, which is relevant to the open loop poles, and angle of arrival, which is relevant to the angle of which is relevant to the open loop zeros. And in the last examples, we extensively discuss this one, and hopefully this will be the simple way to understand. If you have any queries, you can email or text me, or directly you can ask the questions. Okay, thank you so much.